In this video, we will be exploring the equations and the graphs of what is called the uniformly accelerated straight line motion. Now, uniformly accelerated straight line motion is a straight line motion with a constant acceleration. So here the acceleration remains constant vis-a-vis magnitude as well as direction. So the magnitude of acceleration, the direction of acceleration, both remain unchanged in uniformly accelerated straight line motion. So let's consider this x-axis to be the straight line along which this motion is taking place. At time equal to 0, that is when we start the observation, the particle is observed at x0, and then at time equal to t it is observed at x. The acceleration is a, and the initial velocity when we start the observation, that is at time equal to 0, the velocity is u, and the velocity at time equal to t at the final position, that velocity is denoted by v, and the acceleration is being assumed to be constant and equal to a. Now we'll be deducing the equations of uniformly accelerated straight line motion the way we deduced the general equations for straight line motion in the previous couple of videos. So let's start with a being a constant. Now a is a constant and it equals dv by dt. That's the definition of acceleration. Now we bring dt onto the other side of this equation and we get dv equal to a dt. Now remember, a is a constant and constants will stay outside any integrals, any integration that we might do. So now what we choose to do is we integrate both the sides of this equation, and what we now have is, on the left hand side we are integrating dv, on the right hand side we are integrating simply dt. Because a is a constant, it comes out of the integration process. The limits for time will be 0 to t. At 0 time, the magnitude of velocity is u, and when time is t, the velocity is v. On integrating, what we get here is, when you integrate dv, you get v. The limits are u to e, and on the right hand side a, integrating dt we get t, and the limits are 0 to t. Now in place of v we now substitute v and we get v, minus, now in place of v we substitute u, we have v minus u, and on the right hand side we now have a. In place of t, when we substitute t, we have t, and when we substitute 0, we get 0. So this gives us the first equation, v equals u plus a t. The first equation of uniformly accelerated straight line motion. We have derived this now using calculus. In class 9, I guess you derived it in your junior classes. You arrived at the result using graphical interpretations, I guess. Now we've got the first equation here. Now we look for the second. This v here is dx by dt, and that equals now u plus a t. What we'll do is we'll take dt onto the right hand side of the equation and get dx equals u dt plus at dt, and after that of course, we choose to integrate both sides of the equation. Remember, a and u are constant quantities, they stay out of the integration process. Limits for time are 0 to t, and limits for x will be x naught to x. When time was 0, x was x naught. When time is t, x is x. Integrating dx, we get x from x naught to x. Those are the limits for x. On the right hand side, u. When you integrate dt, you get t. Limits are 0 to t plus t dt when integrated gives half t square, or t square by 2. The power here is 1. You increase the power by 1 and divide by the increased power. You get t square by 2. Limits are again 0 to t. Now in place of x, when you substitute x and x naught, you get x minus x naught, the value of this function at the upper limit, minus the value of the function at the lower limit. On the right hand side, you have ut plus you have half a t square. Now this on the left hand side is the displacement, and we get displacement equals ut plus half a t square. That was the equation you used in class 9 as well, in the earlier classes. That's the second equation of motion. And the third one works out a little differently. We are aware that a equals dv by dt. Now what we do is we multiply and divide by dx, and we are very well aware that dx by dt is v. What we now do is we bring this dx to the left hand side, and we have a dx equals v times dv. After this, it's a simple process of integration on both sides. So a integral of dx equals integral of v dv. The limits for x are x naught to x, and the limits for velocity are u to v. When you are at x naught, velocity is u, and when you are at x, velocity is v, as per our starting assumption. So what we end up with now is a x, limits x naught to x. On the right hand side, we have v square by 2, u to v, and so we can take this 2 on to the other side of the equation, and we get here we have v square minus u square, and on the right hand side we have 2. This 2 appears on the other side, 2a x minus x naught, and you will recall that x minus x naught is the displacement, and this v square minus u square equals 2a, s being the displacement here, is your third equation of motion. This is something you learned in junior classes as well. These are the important equations of uniformly accelerated straight line motion. I suggest that you take a screenshot here and make good clear notes of this. We now move on and take up a couple more of the equations which are useful in problem solving. We'll be deducing those equations as well. Now the next equation that we'll be arriving at is the calculation of average velocity in uniformly accelerated straight line motion. Now in a given interval of time, the average velocity is the total displacement during the interval divided by the total time of the interval. So average velocity, which is total displacement by total time. Now the displacement x minus x naught equals ut plus half a t square. Now this here is the displacement and the time of this motion is t. So to get the average velocity, what we do is we divide both sides of the equation by t. So x minus x naught by t gives me, on the right hand side, you divide this by t, you get u. You divide this by t, you get a t by 2. So the average velocity comes out to be u plus a into u plus a into t by 2. Now you can compare this with the first equation of motion, which says v equals u plus at. Now recall that u was the initial velocity, a is acceleration, t is time, and v is the velocity after time t. Now in this equation, if we replace t by 2, we end up with this equation, which essentially tells us that the average velocity during a given interval of time is the velocity at the midway point of the interval, or halfway point of the time interval. So remember this, it's a very important kind of clue to problem solving in straight line motion, that average velocity in an interval is the velocity at the midpoint of that interval, that is halfway point of the interval. Now there is another way of looking at average velocity in uniformly accelerated straight line motion. Now let's try and calculate average velocity as initial velocity plus final velocity by 2. Now this is not going to be true in general, but you will find that this turns out to be true in case of uniformly accelerated straight line motion. Initial velocity plus final velocity by 2 will give us the average velocity. You can check this out. V is u plus at, so we are saying V average is equal to u plus V, which is u plus at, whole thing divided by 2, and we get V average equals u plus a t by 2, which we know is the average velocity. So average velocity in an interval is the arithmetic mean of initial and final velocities of the interval. Okay, so as far as average velocity is concerned, these are two important clues. Average velocity during an interval is the velocity at the midpoint of the interval. Also, average velocity during an interval is the arithmetic mean of the initial and final velocities of that interval. Now, there's more to these sort of problem solving clues, and one of them is regarding the passage of a uniformly accelerated object through 2 points. Now suppose we have 2 points here and they're distant, let's say L, and the velocity here is u and the velocity here is v, and the motion is uniformly accelerated. Now we are looking for the velocity at the midpoint of the interval, midpoint of this run of motion. So this is L by 2, this is L by 2 as well, and we are looking for the velocity v prime over here. Now to calculate this v prime, what we will do is we will be applying the third equation of motion for these two portions of motion. The third equation being v square minus u square equals 2as. So v prime square minus u square equals 2a into the displacement, that's L by 2. That's equation 1. So the 2 of course cancels. For the second half of this motion, we have v square minus v prime square, square of the final velocity of the interval minus the square of the initial velocity of the interval. This equals 2a times the displacement of the interval, that is L by 2 again, and that's the second equation here. Now if you look carefully, the right hand sides of both these equations are same, and therefore the left hand sides must be equal as well, and therefore v prime square minus u square equals v square minus v prime square. On rearranging, v prime comes out to be equal to square root of u square plus v square by 2. So if in a certain motion, in a certain passage of uniformly accelerated motion, the velocities at the initial point and the final points are u and v, then the velocity at the midpoint of that passage, the velocity at the midpoint of that passage will be under root of u square plus v square. So that's an interesting and important sort of problem solving tip. We often come across this kind of calculations in problems. So these are some of the problem solving tips. Maybe I think we'll cover one more here, and that's for calculating the displacement in the nth second of motion. Now I'll have to explain what this nth second of motion really means. Let's say we are looking at a uniformly accelerated kind of straight line motion, and that motion is happening along, let's say, this straight line, the x-axis. Now we observe that the particle is here at time equal to 0 and then it is observed here at time equal to 1 second. Now this displacement here is the displacement during the first 1 second interval of the motion. Now from t equal to 1 to t equal to 2, this is another 1 second time interval, and the displacement during this 1 second interval will be called S2, or the displacement during the second 1 second interval, and so on and so forth. Now when you move from time equal to n minus 1 second to time equal to n second, Again, this is a 1 second time interval. Now this displacement during this 1 second interval is called Sn, or the displacement during the nth 1 second interval. So we are looking for a result for making a calculation of Sn. So Sn is the displacement during the nth 1 second interval of the motion. Now for this nth 1 second interval of the motion, to calculate this displacement, what we'll be doing is, first we'll calculate the displacement in n minus 1 second, and then let's call this displacement as s n minus 1 prime, and the displacement during the entire n second interval, we'll call it Sn prime. Sn, the displacement during the nth 1 second interval, will become Sn prime minus Sn minus 1 prime. Now Sn prime is the displacement in n second. Now in n second, the displacement will be simply u plus u into t, and t being n, plus half a t square. T is now n, so half a n square. This is the displacement in n second. S n minus 1 prime, that is this displacement in n minus 1 second. This is u into n minus 1 plus half a n minus 1 whole square. Now Sn, the displacement during the nth 1 second interval, that will be simply equal to Sn prime minus Sn minus 1 prime. So this Sn will be equal to Sn prime, that is un plus half a n square minus u n minus 1 plus half a n minus 1 whole square. And I leave it for you to make some simplifications, some calculations here, some simple cancellations are involved here. Sn now comes out to be u plus a by 2 times 2n minus 1. So this gives me the displacement during nth 1 second interval. Now I know this language you're probably finding a little confusing, and so what I'll do is I'll make it a little more clear to you with a simple example. Let's say we have an initial velocity of say 4 meter per second and an acceleration equal to 2 meter per second square. Now in 1 second of motion, the displacement from t equal to 0 to t equal to 1, during this interval, the displacement, now this is a 1 second interval, it will be u plus half a t square, and that equals 4 plus half into 2 into 1 square, 2 cancels, and we have 5 meter here. That's the displacement in 1 second. Now displacement from t equal to 0 to t equal to 2 will be again now this will be ut, of course, so t was 1 here. Now it will be 4 into time 2 plus half a t square, that's 2 square. We now have 4 plus 8, and that's 12 meter. So displacement from 0 to 2 for this 2-second interval, the displacement is 12 meter. Now the displacement from t equal to 1 second to t equal to 2 second. Now from t equal to 1 to t equal to 2 second, this is a 1 second interval. But which 1 second interval? The first 1 second interval was from time equal to 0 to time equal to 1 second. That was the first 1 second interval. The second 1 second interval is from time equal to 1 to time equal to 2. Then the third 1 second interval will be from time equal to 2 second to time equal to 3 second. So the displacement of the second 1 second interval will be simply equal to 12 minus 5, and that's 7 meter. This is the displacement during the second 1 second interval. Now we can check this out using the formula we had arrived at. Now for the second 1 second interval, this n has to be 2. So S2, as I have shown here, will be equal to U. Now U is 4 plus A by 2 is 2 divided by 2 into 2 into n. Now n is 2, the second 1 second interval. So 2 into 2 minus 1. Now 2 cancels and you have 3 here. 3 plus 4, that's 7 meter. So this is the equation for displacement in the nth second of the motion. Another very interesting idea related with uniformly accelerated straight line motion is the idea of Galilean ratios. Let me explain to you the idea of Galilean ratios. Now, let's say we have a uniformly accelerated straight line motion happening in which at time equal to 0, the velocity is 0. So we have a motion with 0 initial velocity and a constant acceleration. Let's say the acceleration is 2 meter per second square. Now in this motion, the displacement in the first 1 second interval will be u plus a by 2 into n minus 1. Now this comes out to be 1 meter. Then the displacement in the second 1 second interval will be again u, that's 0, plus a by 2 into 2n minus 1. N now is 2, the second 1 second interval. This time we get 3 meter. Then S3, the displacement in the third 1 second interval. I leave these calculations, maybe I'll calculate this time. So 2 by 2 into 2 into 3 minus 1, and what do we have now? 5 meter. So similarly, displacement S4 during the fourth 1 second interval will be 2 by 2 into 2 into 4 minus 1, and that's 7 meter, and so on. S5 will be 9 meter. I'm sure you can see the pattern now. S6 will be 11 meter, and so on. Now, the ratio of these displacements in successive equal time intervals is 1 is to 3 is to 5 is to 7 is to 9 is to 11. That's the odd numbers, the odd natural numbers. So in a motion with 0 initial velocity and constant acceleration, the displacements in successive equal time intervals are in the ratio 1 is to 3 is to 5 is to 7 is to 9 and so on. This set of ratios is called Galilean ratios. Now I have mentioned here successive equal time intervals. I haven't really mentioned 1 second intervals, whereas over here in this calculation I have shown 1 second intervals. But does it hold if the intervals are larger or smaller? Now we can easily check this out. What we can do is we can take up 2 second intervals. So if we add the first 2 second of motion, that gives us the displacement in the first 2 second interval. Now that is 4 meter. In the next 2 second of the motion, the displacement is 12 meter, and in the next 2 second of motion, the displacement is 20 meter. And what's the ratio again? 1 is to 3 is to 5 and so on and so forth. So even if we take a 2 second interval, the same ratio works. If you picked up larger or smaller intervals than 1 second, you still end up with the same ratios, they work. And this is the concept of what we call Galilean ratios. So what we have done in this video is we have described the equations of motion. We have also seen some basic kind of properties, you can call them, of straight line, uniformly accelerated straight line motion. We've studied about Galilean ratios, and we've had some problem solving tips. We will be using them in the upcoming videos when we take up examples on problem solving. But before that, we have to have a good look at the graphs of uniformly accelerated straight line motion, and also we have to learn how to do problem solving using analysis of graphs. So that's all for this particular video. In the next one, we are taking up graphical analysis and study of graphs of uniformly accelerated straight line motion.